Hello everyone, I'm Norman Wahlberger, and thank you for joining me on this exploration of mathematics. We're looking at solving polynomial equations. We've introduced a new way of thinking about the quadratic case using power series rather than radicals. And we've moved to the cubic case where we've gotten some initial interesting kind of formulas. So we started off with this as our cubic, t plus c1x plus c2x squared plus c3x cubed. So we had replaced the earlier c0 with t for convenience because our orientation at this point is to look for a solution which is a power series in t. And we tried x equals the sum of powers of t up to t to the 7 with some undetermined coefficients a0 up to a7. We saw that one of the conditions on a0 was that it was actually equal to 0. And if we looked at that path, so a0 equals 0, then we were able to uniquely solve for all of the other subsequent values of a. And here are what we got. We got a1 equals minus 1 over c1, a2 equals minus 1 over c1 cubed times c2, and so on, involving powers of c1, actually odd powers of c1 in the denominator. That's actually familiar. That's the same kind of thing that was happening in the quadratic situation. And then we got in the numerator these polynomials in C1, C2, C3, these coefficients that are appearing here in the original cubic, along with, of course, t. Now we want to make sense of this, okay? So this is an interesting thing that happens in mathematics quite a lot, where we've gotten some results of a computation or maybe a series of computations. We have some data, typically in this case a family of expressions, and we want to see what the pattern is. So that's so important to be able to look at something and to say, okay, what's the pattern here? How can we predict what's going to happen if we extend this? For example, if we went a couple of degrees higher, say introduced a sub 8 times t to the 8, we would expect to get an a sub 8, a formula for that. Can we predict what the formula for a sub 8 would be? Okay, so it's like a Sudoku kind of challenge. It's a separate little investigation that we now have to stop and pause and try to figure out what the pattern is here. Okay, so what do we know? Well, we know that the first entries in these polynomials here in the numerator are the Catalan numbers. Okay, the 1, 1, 2, 5, 14, 42, 132. So that part of it is known. And that also emboldens us because it means that that part of the pattern has a nice expression or a nice formula that generates it, and that makes us hopeful that maybe the rest of the pattern could also be explained with some, say, pleasant formula. Now the Catalan numbers are appearing as the coefficients of powers of C2, just pure powers of C2. The other terms, which we have now yet to explain, involve also the variable C3. All of them involve C3, and then also C1 and some C2s as well. So we want to figure out two kinds of things here. Let's write this down. So we want to figure out what kinds of terms appear in one of these numerators. Right? Like, why do we get c1 squared, c2 squared, c3 squared, and not some other thing? Why do we get c1, c2 to the fourth, c3, and not some other thing? Why do we get exactly these three things in addition to this power of c2? And we want to figure out what are the coefficients that appear with these terms. In other words, why does this term that's appearing have a coefficient of 180 in front of it? What's the significance of 180? Okay, so these are two great problems, and if you're really keen, you might like to pause the video for an hour or a day or a week, okay, and see if you can, just from this data here, if you can figure out what the pattern is. It might be that, we'll be tempted to find some more data, like to push this up a little bit to redo the calculation, going up some more terms so that we actually get more data, so we can see more of the pattern, making it a little bit easier to see what's going on. But let's sort of see what we can deal with here. Okay, so what can we say about these things here? Well, let's say start with this one. This is the first one that appears. C1 times C3. Okay. And then this one is C1, C2, C3. And then here we have C1 squared, C3 squared. Here we have C1, C2 squared, C3. C1, C2 cubed, C3, C1 squared, C2, C3 squared. Are we seeing any kind of pattern? Yes, we are. It appears that the terms involved in, say, A sub k are all of the same degree, the same total degree, okay, total degree. Namely, what is that total degree? So A5, all the terms appear to be of degree 4, namely k minus 1. So let's just check. So with A7, all the terms are of degree 6. Yes, they are. A6, all the terms are of degree 5. A3, all the terms are of degree 2. A2, all the terms are of degree 1. A1, all the terms all in the numerator are of degree 0, in other words, constant. So yeah, that jives with the data that we've got so far. But not all terms of that total degree are appearing. So, that's one possible expression in the C's that is of degree 4, but we could also have, say, C1 times C2 times C3 squared. That's not appearing. Why is it not appearing? Well, now you have to do something that that mathematicians, routinely have to do. You have to try to stare at this and try different things. Okay, you just say, okay, you assume that there is some kind of pattern. Okay, that's usually the working assumption, and you have to sort of see, well, what could it possibly be? Maybe there's some relatively simple thing that explains why these terms are appearing and not the other ones. Okay, so to see what that might be, let's look at, say, A6. Okay, C to the 5th. C1, C2 cubed, C3. C1 squared, C2, C3 squared. So one thing that you might eventually come around to realizing is that these terms all have an additional property. Namely, that if you take this exponent here, this exponent is 5, and you look at the index, which is 2, the product of 5 and 2 is 10. Okay. If you look over here, the products of the indices and their exponents are what? Here there's a total of 1. Here there's a total of 6, namely 2 times 3. And here's a total of 3 because the C3 is appearing with an exponent of 1. So we're having 1, 6, and 3. Now 1, 6, and 3 totals to 10, which is the same total that we got here. So what about this one here? C1 squared, so that total would be 2, like if you multiply the degree times the index. Here we have another 2, and here we have a 6. So that's also 10. So all these terms here have the property, in addition to the one that we've just mentioned, that in addition, it appears that we have to now introduce this kind of new concept of degree, right? That's sort of what what's suggested here, that we want to define this new concept, which is not a degree, but it's some kind of souped up degree that involves the real degrees and also the indices. Okay, so let me remind you, the indices here are really coming from the coefficients here and where they fit in the original cubic equations. That's C1 is the coefficient of x, C2 is the coefficient of x squared, C3 is the coefficient of x cubed. So these these indices here really are quite intimately connected with the algebraic nature of the problem. They're not just sort of random. Okay, so often indices are maybe kind of sort of random. You just say, well, let's let this one be A1 and this one be A2 and this one be A3 and so on. But that's not what's happening here. They're actually the indices are closely connected with the actual position of these objects in the thing. So it makes sense that some formula involving the degrees and the indices, might conceivably have some value, and that's what's appearing here. So let's define that the following quantity. Let's give it a name. What should we call it? Okay, it involves indices and it involves degrees. Let's define the index degree. How about that? Okay, this is maybe the simplest thing I can think of. The index degree. Where is our bold? Bold. I think my tool with bold is not around here. Let's view. Maybe I can just do it directly. How do I make a bold? I need another toolbar. Let me just have a look here. Another toolbar. Editing sounds reasonable. Where's the editing one? Oh, it's down here. Okay, I know. Okay, there it is. I need to put it somewhere. Let me put it up here. Whoop. So when you first open Scientific Workplace, these things up here are not populated. So these are tools, and they're obtained from view here, toolbars. You see these toolbars here? You click that, and you have a whole list of toolbars, and the ones that I've checked are the ones that have appeared, and I've been able to put them where I want. Okay, you may have to do something like I did, sort of manipulate them a little bit. But now I've just added the edit tool. There it is there, and that one there, it allows me to make something bold. So I'm going to put B for bold, and there we get a nice bold. So I like to make my definitions in bold. That's a relatively simple way of denoting the fact that we're defining something. So define the index degree of a term. Okay, now I don't want to continue with that bold, so let me make that normal. Okay, so what's the general kind of thing? So suppose we have, say, C sub 1 to the power, M sub 1, okay? And then something with C2 and something with C3. So I'll change these 1s to 2s. And this 3. Whoop. C sub 3 super M sub 3. Okay, so there's a term consisting of C1s, C2, C3s. We'll define the index degree of a term thing to be the sum of the products of the indices and the degrees of each of the constituent variables, i.e., in this case, it would be 1 times M sub 1 plus 2 times M sub 2 plus 3 times M sub 3. Okay, that's the index degree of this term. And we're claiming, in addition, appears that the following quantity, namely that thing, is constant in each expression, in each of the AIs, let's say. Let's check that with the other ones just to make sure that's true. Okay, so for A3, the index degree here is 2. The index degree here is 1 times 1 plus 1 times 3. Sorry, the index degree here is 2 times 2, that's 4. The index degree here is 1 times 1, and 3 times 1, that's a total of 4. Yes, so the index degree of all the terms here is 4. The ordinary degree of both these terms is 2. The index degree is 4. How about over here? The index degree is 6, and here we have 1 plus 2 plus 3, which is also 6. The ordinary degree is 3. Here the index degree is 8. 2 plus 6 is 8. 1 plus 4 plus 3, that's also 8, while the ordinary degree is 4. So it appears, let me add this, it appears then that the index degree is always exactly twice the usual degree. Okay, let's carry on, just checking if that's true. So for A6, we have degree, index degree 10, index degree 1 plus 6 plus 3, which is also 10, and index degree 2 plus 6, which is also 10, which is twice the degree, which is 5. Okay, and for A7, index degree of 12 for this one, 3 plus 9, that's also 12, and here 2 plus 4 plus 6, which is also 12, and here 1 plus 8 plus 3, which is also 12, and they all have degree, otherwise 6. Now, are we getting all such? We've said that all the terms that are appearing here are of degree, whatever they are, and of index degree, whatever they are. So for A7, the total degree was 6. So let's say, so the total degree, or the usual degree, is k minus 1, while the index degree is 2 times k minus 1. So when k is 7, the usual degrees are 6 of all these terms, while the index degree is 2 times 6, which is 12. But do all terms that have this property actually appear? So each of the terms that are appearing here has this property, that the degree is a certain thing and the index degree is something. But maybe there's some other term that's not on this list which also has this property. Or are these exactly the 4 terms that have the property that their index degree is 6 and their usual degree is 6 and their index degree is 12? Okay, so that's something that we would have to kind of check, and I'm going to leave this as a little exercise so you can question, is this the case? So if it is, then we're in a kind of a happy situation, because then now we've sort of solved half of the problem that we wanted to understand. We want to understand which of these terms appears, and now we have a kind of a reasonable a guess at least as to how to predict which kinds of terms are going to appear for one of these A's. Great. Now the second part of the problem is to figure out the coefficients that are in front of those terms. So now we want to understand the coefficients. And perhaps the first thing to do is to observe that whatever coefficients are happening here, some of them have plus signs and some of them have minus signs in front of them. So that might be a first thing to figure out, which ones have the plus signs and which ones the minus signs. There's a little bit of inconsistency the way we're writing things here because there's minus signs in front of all these ones except for this one. So let's just adjust this so it's a little bit more in keeping with the other things. So Scientific Workplace just has some automatic default ways of expressing things, and sometimes you just have to adjust so that things are looking a little bit more consistent from your point of view. So now things are a little bit more consistent. And now we can ask, okay, there's these minus signs in front here, but say in these terms here, which terms have plus signs in front of them and which ones have negative signs in front of them? So how about the negative signs? Here there's a negative sign in front of C1 and C3. Here also in front of C1, C2, C3. Here in front of C1, C2 squared C3. Here in front of C1, C2 cubed C3. Here in front of C1 cubed C3 cubed. And here in front of C1, C2 to the fourth C3. It appears, it appears that the sign of the terms is determined by, well, I think it's not too hard to figure out what it is, at least sort of what it's suggested. It's C1 which is controlling this. It's determined by the power of C1 appearing in the term. If there is an even power, then we get, well, it depends on whether we're including this minus sign, but if we're just looking at these terms here, an even power, then we, for example, this one here is an even power. No, this one here is an even power. It looks like we get a plus sign, and with an odd power, we get a minus sign. So this is not including the common minus sign out front. Okay, just so we don't get confused. So I think it's reasonably, we have a reasonable guess as to what determines the sign. So that's also making us more confident, right? That there is a pattern here. It's not just some kind of random thing. It's not like we're talking about prime numbers, you know, with some kind of randomness. No, it appears that there's perhaps some kind of formula here. So now we have to get to grips with the actual numbers that appear. So to get to grips with the numbers that appear as coefficients, let's first just write them down in a nice way. So there's a kind of an array of numbers here. It's kind of a triangular, right? But these numbers, these coefficients are getting a little bigger as we go down. So we're going to use a matrix to do that. Now, one way of doing a matrix is to use this sign right here. You see this symbol here? So if I pop that up there, then I get a possibility of creating a matrix of a certain dimension, and that's quite useful. But I'm going to do it in another way. I'm going to go to the Compute tab here and go down to Matrices. Okay, and you see that there's a whole bunch of tools for matrices. So you can learn a lot of, say, linear algebra just by playing around with these tools. Okay, but we're going to go to Fill Matrix. So we're going to create a matrix of a certain size that's filled with something. Okay, and let's fill it with zeros to start with, just so it's filled with something. And how big is this thing going to be? Well, we're going down to 1, 2, 3, 4, and then 3, and then this one also has 3, and then this one has 2, and then this is 1 and 1 and 1. So it looks like maybe, well, there's seven of these, so 7 rows. Okay, maybe make it 7 rows, and it looks like we're going to have 4 columns. That might do the trick. And okay, you can see there's that matrix. I'm going to just move it actually for convenience, just temporarily. I'm going to move it up here somewhere, so I can manipulate it and fill it in with the things here. I'll put a few spaces. Okay, I also prefer to have my matrices with parentheses, so I'm going to go to Properties. This magnifying glass is Properties, so now I can adjust the look of this matrix. It looks a bit more like a matrix now to me. Okay, so I'm going to populate this with the coefficients, with just the coefficients that are appearing. Okay, there's a 1, there's a 1, and I'm going to ignore the signs. 2 and 1 appearing there, and then on the next row we have a 5 and another 5, and then a 14 and a 3 and a 21, and then a 42, an 84, a 28, 132, a 12, 180, and a 330. Okay, that's really capturing the coefficients that appear. And the first column of this we are happy with. Those are the Catalan numbers. Now, as for these other ones, along each row, the numbers are determined, but the actual order along the row is a little bit random, right? A scientific workplace has just spewed out these polynomials in some fashion. It's not entirely clear what the mechanism is, but we don't have to concern ourselves with that. We just have to recognize that this is not a God-given order. So it might be that it's convenient to rearrange the entries along a given row, okay? So let's grab that again and bring it down here somewhere. Okay, and now for the coefficients. Okay, there's that matrix. So we want to come to grips. We want to explain what are these things. So the first column are Catalan numbers. And I remind you that they are like what we call C sub n, and that was fraction 1 over n plus 1 times the binomial coefficient, which is down here. Binomial coefficient 2n, choose n. And if we want to write that out, it's the same as a 2n factorial divided by n plus 1 factorial times n factorial. Okay, what are we going to do? Well, we have to stare at these numbers. Okay, we have to see if we can, make some sense of them. And one natural thing to do is to look at the factorization of these numbers into primes. So that's a general kind of idea that you can do. If you're looking for some formula, if the formula is going to involve factorials or products of factorials or something like that, then the prime power decomposition of the numbers is something that's going to help you in identifying that. So the advantage in having them all here in a matrix is that we can factor them. We can factor them all at the same time. And now we are kind of happy because look at the factorizations. Even though some of the numbers are big, the prime factors that appear are all relatively small. In fact, the highest prime factor is 11. 2 times 3 times 5 times 11. Here we have 2 squared, 3 squared, 5. 2 squared, 7. 3 times 7. 2 squared, 3, and so on. So this is quite nice. And now this suggests that a formula like this, a Catalan type formula, might very well be explaining these additional coefficients that are appearing here. So that's good. We're happy with that. We want to find such a formula. So for that, we want to go back to our list of actual numbers. And stare at them a little bit more. So what we want to do is we want to associate, these numbers here with these terms. So we know what the first column. So what I'm going to do is I'm going to just sort of put the relevant pieces of data together. So I'm just going to put the terms that go with the numbers beside the numbers, so we can kind of stare at them. Maybe that'll give us some kind of clue as to how to get the numbers from the terms. 21, that's that one there. The 84 was this one here. And here. And Okay, so now what we want to do is we want to try to explain the numbers that are appearing here in terms of the terms. How can we predict that this is going to be 3 times 7 from this? So let's go down this column, since we sort of understand this column, and maybe it's actually helpful for us to actually put that first column in as well, right? So that there's C2, and then there's C2 squared, and C2 cubed, and C2 to the 4th, and all the way up to C2 to the 6th. So now we've got all the information. So we shouldn't disregard this, because this is, you know, what we know about. So whatever connection that the 5 has to the C2 cubed might give us some insight into, you know, these other ones.